All right, welcome back, Precalcsters. Today, we're going to be rational about stuff. Specifically, we're going to be rational regarding our functions. Rational functions. All right. So, these are awesome. You're going to disagree with that initially, but it's my hope that over the next day or two, I don't even have notes, I don't know why. Over the next day or two, I can convince you guys similarly that they're awesome and they're easy and way easier than you might think. First of all, what is a rational function? What's a ratio? We'll say that louder. I'm going to close that door because it seems like they're having PE inside or lunch inside for some reason. All right, so somebody gave me an F word a second ago. I think I heard it. Fraction. A ratio is a fraction, which means a rational function must just be a function with a fraction. Okay, so pause. So we'll define it. I'm going to define it right here. Rational. I would never write the word rational ever. What is the shorthand for rational? The blackboard what? Is real, but I like it. Fractions are just division, right? And division is quotient. Quotients, Q. Rational is the blackboard Q. It's just a regular Q. Here's what my capital Q's look like. It's just that or that realistically. I just do this and then I make it fancy. Not a circle with an H, it's a blackboard Q. Okay, now a rational function then, if we say that ratios are just fractions, you're naturally led or pushed, however you want to think about it, to saying it's a function with a fraction. Pause, because I want to be really specific. I'm going to write a function with a fraction, and I want you to tell me, is this a rational function? It is not. That's a good question. This is a linear function. Like, I know that's true. Just saying it's linear is enough, realistically, to say it's not rational, because rational functions won't be linear. But there's a difference and something really specific we have to talk about. So remembering the fact that ratio or rational means fraction is the first part. We're just going to say rational function, and we'll just define it easy, has the form f of x equals, and I'm going to use some very specific letters for this. I'm going to use capital letters just to specify. We have n of x over d of x. Why do you think I have chosen to use n and d? The numerator and the denominator. Now, this thing, you might be tempted to say this, is still irrational because I think one could arguably write it like this. Is there a very clear numerator and denominator? Yeah. This is a constant function. Is it really and truly a function in terms of x, though? There's no x here. We're going to say numerator and denominator with, or where rather, each has variables. And I'm going to use our calculator shorthand, vars. The fact that there's no variable in the denominator of this one over on the right side means that it's not a rational function. The ratio part, we need that x in the numerator and the denominator. Okay, now, immediately we can start talking about the key characteristics of these, and I'm going to organize this differently probably than I ever have before, and that's okay. So let's talk about some key features of these types of graphs. Now, we've not used this language like consistently, and I don't think it really matters at this point, but some key features, some important features, if you will, of functions that we've seen. We've talked a lot about them. Do we care typically where y-intercepts happen? If you're graphing, do you usually show it crossing the y-axis? Yeah. Other key features that you guys can think of? The x-intercepts are a huge one, right? Because we literally just spent 3 days learning how to find the x-intercepts better of bigger functions. Extrema, are those key features or characteristics? Okay. Any other ones that maybe I've had a student teacher that annoyed me that we haven't seen yet, but maybe they show up? Asymptotes. What is asymptota? Let me say that like a human. What's an asymptote?
It's the never approaching like the.
It's where they can never approach a certain number.
Okay, we're going to clean that up. You're right, just so you know. But we're going to make that language better. Now, as we're looking at these, key features and characteristics, we'll get to asymptotes here shortly. But the easiest one is to deal with here, domains. Now, for whatever reason, I don't know if it's just some degree of abstraction, which just means like something that we just represent with ideas, right? That's a lot of math. It's a whole lot of abstract thinking because we don't have physical x squared objects in front of us. We just deal with x squared as we understand that it exists somewhere. Okay, domain. Easy questions or hard questions for you historically? If I said, what is a domain? Is that an easy question or a hard question for any random function to give you? Easy. What is a domain? Like just in general, what is a domain? The set of all x's, or if you'd rather, we could say the set of all inputs, right? Now, for this, there's only a few things right now that we've discussed that we have to worry about. I'm not going to redefine this as a set of all x. For a rational function of this form, there's only one thing that I think could break it. We will never have a square root in this because we have polynomial functions. Nice numerator, nice denominator, no square roots. So I don't have to worry about taking the square root of a negative and breaking it. There's only one other thing that we have to worry about that breaks stuff. Zero. What about 0? They divide out, right? Or if you divide by 0, it's broken. So the domains of rational functions that look like this, all we have to worry about is we're just going to make it really easy. It is typically, if we're working with x, it's going to be the set of x such that x is in R. So it's a real number right off the bat. And what's the denominator of any arbitrary rational function? What do we say it? So d of x, just to like really clean it up, are we all agreed that's the denominator? What can't it equal?
0.
We just need to find what makes me divide by 0 and get it out of there. That's it. Okay. Now, right off the bat, these things, some other key features, and we'll look at this. The shape of these is a little bit ambiguous because it varies. Most commonly, we refer to these as hyperbola. A hyperbola. Now, we'll sketch a really easy one, but we'll just say graph. For the parent of these, the most simple, graph is hyperbola. And we're going to clean up a little bit of stuff, and we'll talk about what I'm going to clean up. And actually, we're just going to do it right now. I'm going to go back and I'm going to make one little change just to clean up this language because immediately I was trying to make this simpler, but we missed one little part. I don't really care that each has variables, but I do care that the denominator has variables because otherwise it's just linear. So I went back. The numerator doesn't have to have a variable, but the denominator must. Okay. And the reason that I'm bringing that up is when we talk about the hyperbola, there's a really easy one to think of. Okay, without making a table, you guys are going to help me plot some points. We're going to graph a single easy parent function here. I want us to graph on this. We'll use f of x, I suppose. F of x equals 1 over x. Is there any value of x that I can't pick? 0, because that's the 0 of the denominator, and it makes me divide by 0. Okay, so give me some easy x values that we could pick. 1. If I plug in a 1, what's 1 over 1? 1. So I get 1 comma 1. And I'm not even going to put a scale on this. Pick another number. 2, and it's 1/2. Pick another one. Okay, I'm not going to let you pick any more big ones because I'm getting too close. Like, I'm getting close to 0 there, right? Let's get closer. What's 1 over 1/2 instead? 1 over 1/2? 2, because it's 1, and then we do the hollow O, and we multiply by the reciprocal. What's 1 over 1/3 if I get closer? 1 over 1/4? This thing just keeps getting bigger and bigger and bigger as we get arbitrarily close to where x equals 0. Same thing, it gets arbitrarily close to y equals 0 as we pick a bigger number. Like, I don't really care if somebody gives me 1/1 trillionth of a dollar, but it's still better than nothing, right? Like, it's not quite nothing. It is for all intent and purpose of it, but sure. Okay, give me some other ones over here. -1. What's 1 over -1? So -1 -1, okay, cool. And we're going to see something very similar happening. Okay, this is the general shape of these graphs. It is not always going to be like this because we can make them wonky. We can give them more asymptotes than this. We can give them different types of asymptotes. But this is, in general, what is known as a hyperbola. Cool. Everybody all right there? Sweet. Okay, looking past this. When we have these, we're going to think about domains, the graphs. I'm fine with that. The end behavior is going to be kind of its own big section. So these are the basic key features, but we're going to dive in a little bit more hardcore than this. When we talk about the end behavior of these, I'm going to sneak this in as a larger section. Let's talk about the asymptotes. Okay, now, I probably could have snuck this in as a definition. You guys have seen the word asymptote before. You have a general idea of what it is, and we don't need a real formal, rigorous definition here, but I do want to make sure that we can make sense of it. There's really three, but there's two flavors of asymptotes that you've experienced or seen before. Give me one of them. Okay, I'll give you one of them, and you'll give me the other. The first of these, asymptote, we can say that, hey, there are these things called horizontal asymptotes. Now, we will define this, and if we have to write stuff down, I'm happy to do so. Can you guys give me, without giving you the challenge of doing it, thumbs up if you know what asymptotes are? You might struggle to explain it, but you can imagine and you conceptualize what it is. Thumbs down if not a clue and you've used it. Okay, so we're going to sneak in here. Horizontal asymptotes, and we're going to define each of them. For these, we are thinking of a horizontal line. A horizontal line which my function, or I'll say my function, I'm fine with that. My function gets arbitrarily close to, and we're going to pause there for just a second. If I say arbitrarily, what on earth does that mean? So arbitrarily just means, when we say arbitrarily close as we want. So for example, if I want to get close to 1, is 0.99 pretty close? Can I get closer than 0.99? Yeah, I can do 0.999. Could I get closer than that? Now, is that ever going to stop? No, arbitrarily, as close as we want, we can get there. So when we're thinking about a horizontal asymptote, it is simply a horizontal line which my function gets arbitrarily close to as x goes to the end. Now, I'm going to write goes to the end in much more mathematical notation. You guys are looking at me. I'm a number line, and I'm the origin. Look at me. How far do my arm need to go if it goes to the end? Infinite. How far does my arm need to go in the negative direction to get to the end? Negative infinity. So really, I just care what y value does my function get really close to as x gets really big or really small. Positive or negative infinity. Okay, we're not going to write it down, but warning, I don't care at all about the middle. I only care about the ends. I can cross these in the middle of my graph. I don't care. We care about the ends. This we've seen before, and I'm just going to put it here. And I was expecting more shocked looks out of the robot voice, but I'm cool with that. This is simply end behavior. This is it. Now, these functions are fundamentally different. They don't go to infinity or negative infinity if they have a horizontal asymptote. They mellow out at some number. For example, this is a pretty lazy graph of 1 over x, but I think you can tell me. If I go towards the end, so all the way over here, what value am I getting really close to in the y? I'm getting really close to y equals 0, but I'm never quite getting there. I'm getting how close, might we say? Arbitrarily close. Okay, as I move to the left, what do I get arbitrarily close to as I go further out? 0 again, right? It's just the negative from the negative side, so it's a negative number. But if it's really a trillionth or a billionth or a trillionth, it doesn't really matter if you're above or below. It's really close to it. Okay, these are horizontal asymptotes. On the other side of things, or in a different dimension, if you will, and that works way better and it's actually accurate, a different dimension from horizontal, it's a vertical dimension. We also have vertical asymptotes. Now, you will undoubtedly see me write these again. However, I'm going to try my best not to. We have shorthands that we're going to use. Horizontal asymptote, anybody have a suggestion for what we might shorthand this with? Ha! You're correct. Ha! HA. How about this one? That one does not work as well. HAVA. Horizontal asymptote, vertical asymptote. Embrace the shorthand. Otherwise, embrace 10 letters over and over and over and over and over. There's way more than 10 letters there. I don't know. Okay. How would you define these ones? So it's natural to want to use the same thing and just change it, right? And we can use bits and pieces of it, but it might be a better way. Not necessarily, but it might be. Instead of saying a vertical line that my function gets close to, let's just think about this. If I have a vertical line, like does this have a vertical asymptote?
Yeah.
And where is it on this graph? At x equals 0. So we're going to say as x gets really close to my vertical asymptote, my function either blows up, which is increases without bound. That goes up to positive infinity. Or is this going to infinity? It's going to negative infinity. Or it decreases without bound. So we're going to say a vertical asymptote is a vertical line. A vertical line where my function increases or decreases without bound, which that's my fancy to infinity or negative infinity. A vertical line where my function increases or decreases without bound as x gets arbitrarily close. Okay. Our discussion on Monday will begin with not just these statements, but it will begin, lots of words one time. It will begin with how do we find the vertical and horizontal asymptotes in a systematic, easy to work through way. Okay, I'm going to break your hearts. No homework. You can be convinced otherwise.